I see many guys from civil engineering. I'm sure they will.
May I ask two questions?
Yes, of course. Hi. Yes.
Very nice talk. Thank you very much. Unfortunately, I missed your beginning part. I have two questions related to your simulation. Could you please explain to us what is the essential advantage of the Stockwell transform in comparison, say, to Laplace transform or Fourier transform? This is the first question. Okay. And the second question is...
Perhaps I may start with the answer to the first question. In order to I would I would like to avoid to forget the first question when you ask the second one.
Okay,
That's why, if it's okay for you.
Yeah, it's for me too. It's no problem. Yeah.
So if I come back to to this work, as you can see, for instance, as you can see here, the main advantage of the Stockwell transform is to move from this time domain signal to this time frequency domain signal. So if we take this signal, for instance, you can see that between 30 and 40 seconds, we have a large amount of the energy concentrated in this time window. But as you can see also, we have low frequency components here, but we also have higher frequency components here. And these higher frequency components may be identified here or around 0.4 Hertz, and they are in the time window between 25 to 30 seconds. So it is very easy with such time frequency transform to identify the amplitude of the seismic excitation in the time domain in a given time window, but also for a given spectral component. So that is the main advantage of time frequency transforms.
Okay.
Then there are various types of time frequency transforms. The Stockwell transform is very efficient because it preserves the phase of the signals. So it is very important, especially in the field of seismology, to preserve the phase of the signal.
Okay. I mean, I never use this method, therefore I'm not familiar with this method. Okay. So,
probably you may be interested by our paper on the Normalized-Inner Product and the Stockwell transform.
Okay.
It was published in the BSSA in 2015.
Okay. Very interesting. Another question is related to your boundary element implementation. You have mentioned you have used half space and the Green's function. Is this 3D or 2D simulation in your boundary element simulation?
These are 3D simulations, and especially for 3D simulations, we need accelerated boundary element formulations because in fact, if we use boundary element methods, we save some degrees of freedom because we only discretize surfaces in the 3D space, but we get unsymmetrical, fully populated matrices to solve in our linear system. So in order to reduce the complexity in both CPU and memory storage, we developed several years ago this fast multiple boundary element formulation. And more recently, we started to work on H matrices boundary element formulations, which are even more efficient than fast multiple boundary element formulations.
Yeah. Can you get a closed form half space Green's functions, or you have some infinite integrals in 3D?
For the fast multiple boundary element formulation, you mean?
Yeah.
Yeah, the closed form solution. So it is not a personal work. It is a work by my colleagues Stéphanie Chaya and Marc Bonnet. They published a paper on this this very topic. I think perhaps 5 years ago or 6 years ago. And this is a closed form solution, but it is very, very complicated.
In terms of infinite integrals, I think you have three, integrals here from infinity to plus.
So I may send you the reference of this paper by Stéphanie and Marc on the half-space Green's function for fast multiple boundary element method.
Great, thank you. Okay, thank you.
Thank you very much. Do we have more questions? Maybe I will continue, and don't hesitate if you have a question to ask it. So Jean-François, in your actually that was the last slide of the part 2, just before starting. So you were talking about this homogenization of the pillars. I was just wondering when you do exactly. So you said you homogenize this and you have an effective what is this color? This is, I don't know the color, but anyway, this is these pillars that you have on the surface. So you keep the same height, right?
Yeah. In this
for
case,
the effective, and basically you just do this here. It's periodic, so you do this usual homogenization. You don't have any additional boundary element that you would add in the beginning of this material or at the interface between the two media.
In fact, we have a transition between the homogenized part and the free surface here. So we have an impedance condition at the surface in this part only, and then we have a free field condition in this part. So we have to connect both parts of the model in the framework of a numerical method. In fact, if we want to consider a finite extension of the city, considering the uniform height of the buildings, we may consider a periodic city with different building heights, if we want. And then we may define a specific cell with several buildings with various heights, but repeated periodically. And then we may investigate the influence of this height variation within a given cell or building blocks, let's say.
And if you do this homogenization with different heights, will you at the end get an effective block, or you will get not a block anymore, but still like a discontinuity in your homogenized geometry?
Yeah, we'll get an effective block.
Effective block.
Then we may also consider two different cities apart one from each other, and then consider an effective condition, and then a free surface condition in between, and to see the influence, for instance, of the waves radiated by one city, surface waves propagating towards the other city, and the interaction between two cities, for instance. It is also possible. But in this case, at the top, we have let's say the closed form solution in the case of an infinite extension city, and we combine with the numerical method in this case of a finite extension city.
Okay, good. Thanks. Is there more questions? If no, then I will have I have actually
quick
question. You have a go ahead.
Mohamed. Okay, just a quick question. I was wondering if you can come back on the clocking effects and the example you showed us. I'm wondering if is it your clocking effect due to inertial amplification or of your structure, or some other elements of a structure, or other, if I can call them like this, a phenomenon like mass density or other periodic effects? It's due to, so is it local or periodic effects, behavior of structure? I see the structure in the example.
Yeah. Okay.
Explain
in fact,
more about the clocking.
Sorry. Okay. Yeah. In fact, we have various effects. We may have, depending on the building features, we may have some kinematic effect at the interface, but mainly for body waves. We may have some inertial effects, but it depends also on the, for instance, rocking of the structure. And we may have also some interactions due to surface wave propagation and generation. We may have we have surface wave generation at the basin edges, but we also have surface wave generation due to the lateral heterogeneities between this surface free surface area and this area where the stiffness or the mass are different due to the presence of the building. So in fact, we have three effects: kinematic effect, inertial effect, and surface waves in interaction with the surface wave generation process.
I see. Okay, thanks, Mohamed.
Yeah, actually, I have two other questions, small questions. At the end of your talk, you were showing a pulse propagating through the structures, and then you were showing the case that you have homogenized and that the signal was more or less the same. And I was wondering, I cannot get the feeling of, maybe you show it first. It was a pulse, and then one through the real structure and one through the homogenization.
Okay, at the end of this.
Yes, it was at the end.
Okay.
And the question is, for the worst frequencies, like to the highest frequencies, what's the wavelength compared to the size of your buildings or your smallest structures?
For the highest frequency for 3 Hz, you mean?
Yes.
Yeah, more or less, it is possible. It is more or less possible to identify the wavelength on the plot itself. As you can see here, we can see the wavelength of the wave here. So it may be larger than the building width, but smaller or of the same order than the building height. But we have to consider that the seismic waves are mainly body, either pressure or shear waves or surface waves. And we also have to consider that for the buildings, we may mainly have bending or rocking. So it is a different kinematics.
Okay, I see. And then a question related to this. So you have this, you called it enriched kind of elasticity, that the enriched model. And I was wondering how close is this to stuff like micropolar or micromorphic elasticity? If you would,
it is in fact very close to such approaches. Okay. It is mainly adapted to discrete models, but it may be used for perhaps any type of lattice structure. In fact.
Okay. So in principle, with these enriched cases, you would be able to go much higher in frequency and even to catch some resonance, like inside of your structures. Yeah,
exactly. Yeah, we mainly developed this enriched finite element model for seismic studies, but it may be used for dynamic excitation even in the higher frequency range.
Yeah, I mean, I see. I mean, here I was a bit confused in the beginning because your structures are not very, let's say, geometrically. How should I say this? They are not responding in in your defavor in the sense that, that you don't have any chiral effects, but actually in buildings you don't have such effects. I think, so very likely you would, with the enriched case, you would be able to catch even some chiral effects in buildings if you would make them chiral in the first place.
Yeah, exactly. Yeah, we may use our model in various configurations, and for the specific topic we just talk about, we only see a part of the interest of such a model.
Okay, thanks. Do we have more questions from the audience? I'm just reading the chat, so no more questions. So if there is no more question from the audience, I would like to say thank you to François again.
Thank you very much for your invitation.
And your talk has been recorded and it will be available, I would say, from tomorrow on our website.
Okay, thank you very much. Bye-bye.
So, thank you very much and bye-bye.
Bye.
Thank you, Jean-François. And see you next week. Yeah, we have Mario Severina from the University of Lisbon. Okay, see you. Stay safe. Bye-bye.
Bye-bye.
Bye-bye. Thank you.